What is long range dependence? If we find a process for which the autocorrelation function goes down very slowly, and when you add up, the sum is infinity, then that is long range dependence. Very simple definition. If the sum of the autocorrelation function is infinity, then it is a long range dependent process. So another definition for the same thing is that if the autocorrelation function goes to k raised to 2h minus 2lk, where k goes to infinity, then we say that this is a long range dependent process with the Hurst exponent of h. Now what is lk and what is all this? Lk is any slowly varying function of x. Slowly varying means it is not going down anywhere very fast. For example, LAX upon LX tends to 1 when x approaches infinity. That is called a slowly varying function. When LAX upon LX goes to 1, then that is called a slowly varying function. The example is a constant. If you take constant function and you take the value at AX or value at X, the ratio remains 1. If you take log function, log of AX divided by log of X, that goes to 1. So if you take any slowly varying function, so this goes basically to 1 as k goes to infinity, and RK, the autocorrelation goes to k raised to some power. This is like a power tail, right? So if it goes to k raised to some power, we look at the power. If the power is 2h minus 2, then we say this has a Hurst exponent of h. So we just have to write down the autocorrelation function and write it down as a power function of k. And everything else will go to 1, but this power function of k is what we are looking for, and 2h minus 2. Now, you can see that if h is greater than 1, obviously this is not possible because then, it will go to infinity, and that is not what is possible. Generally, h will be less than 1. However, the question is whether it is less than half or more than half. If it is less than half, then this will die down very fast. And that will not be long range dependent. If h is more than half, that is the interesting part, then it will go for a very long time. Okay. So now here's the thing. So basically now we understand what is long range dependence and what is short range dependence. The question is why are we learning all this? The thing is that they have shown, the measurements have shown that most of the things that we deal with have a long range dependence. All right, here are the examples. And the reason they have long range dependence is that anytime you take a large number of on-off processes with heavy-tailed on time or heavy-tailed off time, those are the two conditions. Either the time on time is heavy-tailed or the off time is heavy-tailed, that results in a long range dependence. We have lots of things that we have on-off times. So, for example, file sizes. File sizes have been shown to have a long-tail distribution. So, most of the files are small, but there are a few files which are megabyte, gigabyte, and terabytes. Right? So, they clearly can be shown to have a long-tail distribution. When you send the file on a network, what you are doing, you have off time, then there's nothing being sent, and then suddenly you're sending a file, there's an on time. So you have a binary process, on-off process with heavy-tailed on time. So the network traffic has a long-range dependence. So internet traffic is long-range. Connection time. Connection duration when people connect to a network. This is similar to the file sizes. Most of the time you connect for a short time, but sometimes you connect for days. And so that is long-range dependence. Traffic, heavy traffic. Unix processors have been found to have heavy tail distribution. So they measure the time, how long Unix processors live, and they found long tail distribution. Congestion and feedback control mechanisms also increase the dependence in the traffic. Because of the congestion, the dependence of the traffic service depends upon the past. Because here's the thing, suppose you went to a highway and suddenly there's an accident. So there's a congestion. Now, the rate at which people are going to get out going to depend upon, what happened this morning, right? As opposed to if it was no accident, then, basically you couldn't tell anything about the evening from the morning. There's no dependence. But if there's a congestion, then there's a dependence. And so that causes the dependence range to go up. So basically, now here's another interesting part. Is a very easy way to publish a paper nowadays is to take any measurement and show that this has a long-range dependence. Basically, and that's what is happening. Everybody is showing if it is not long-range dependence, you can't publish it. I mean, who is going to publish that the time is exponentially distributed, right? So lots of papers are coming up with showing that everything in the world is long-range dependent. Okay, here thing. First of all, if you have long-range distribution, most of the time you cannot analyze it. So if you want the answer, you have to make a simplification, right? So you have to assume exponential and things like that, right? In some cases, in operational analysis, you don't assume any distribution. So that is long-range independent proof, LRD proof. But other things, which we did, like MBA and other things, they assume exponential distribution. So what you need to do is somehow have an argument or have a proof or have your own belief that this is somewhat close to the reality. Well, here is the thing. Let me take both sides. So a lot of people are showing a lot of things to be long-range independent, but they're looking for it. I mean, so you find it. But I mean, thing is, if it is not long-range independent, we don't publish it. Period. So here's what happens. For example, we did analysis of video traffic, and suddenly we found the long-range independent. Obviously, we put that in the paper. Yeah, this is long-range independent. If it were not, I'm not going to publish it. Nobody will publish it. Nobody will accept it. So it's not that there is no traffic with short-range dependence. There is plenty of short-range dependence, but that is not something that is published. It's like this. I mean, the news is only about killing and violence and all that. Is that the life? No. Life is peaceful, but that is not publishable. No. The thing is, you can use it if you somehow can show that in your case the exponential applies, or you are close to exponential. That's what I just said. Is that all those things are still valid, but you have to somehow justify your assumption of exponentiality. All right? You could just take, whatever sample size you can get and show that, okay, in our case, we didn't have a heavy tail. So, it's fine. I mean, both sides are possible, except that LRD makes the news, SRD does not make a news. All right. If you are going to use SRD, then you have to justify it. You have to show that, yeah, this is short-range dependent. So long-range dependence invalidates all results for the queuing theory obtained using Poisson processes, and the buffer sizes, etc., are way off. So just like this, for 1-digit accuracy, you need 10⁻11 observations. Similarly, the buffer sizes that you calculate with exponential may be way off from what you have with LRD. All right. All right. So now the one thing I want to, before I get more into LRD, is that I want to you to be able to distinguish self-similarity versus LRD. And a lot of people, when they mean LRD, they say self-similar. When they mean self-similar, they say LRD. So a lot of people don't distinguish between the two. That's why I want to make sure. Self-similarity does not mean long-range dependence. Self-similar process can be short-range dependent or long-range dependent. If your H in that formula that we had put there is less than, is between half and 1, then you have long-range dependence. If you have formula with less than half, then there's no long-range dependence. So basically, when you see something which is self-similar, first find out what is the value of H. If H is between half and 1, then you have a long-range dependence and you have a problem. If it is less than half, then there is short-range dependence. All right. So for example, ARIMA PDQ with integer value D is SRD, but ARIMA P delta D plus delta Q with delta being minus half to plus half, fractional value has a long-range dependence. All right. Very simple. If you take a series like 1 minus B raised to D, if D is integer, you will have a finite series. If I put D equal to any fraction, you will have infinite series. Right? When you have infinite series, then there is some relationship, and then depends on how quickly that series is going down. Right? So that's what it is that same ARIMA model could be short-range dependent or long-range dependent. So we will work on the long-range dependent. So we will take ARIMA model. But first, let's see what is ARIMA looks like. So let's look at ARIMA process, and very simple process, 0, 0.25, comma 0. So we have autoregressive order is 0, the integration order is 0.25, and the moving average order is 0. ARIMA, right? Autoregressive, integrated, moving average. And fractional is 0.25. So this model can be very easily written as 1 minus b raised to 0.25 xt is equal to et. If you remember the autoregressive model. The autoregressive part is not there, and the moving average part is not there. Only the integration part is there. In the integration part, all we do is 1 minus b raised to the power d. All right. So this is xt. I could bring this to the other side, and so xt is equal to 1 minus b raised to 0 minus 0.25 et. I could expand this series, and when I expand this, I get minus 0.25 times et minus 1, and then I get minus 0.25 times minus 0.25 times minus 1 divided by 1 and 2, and so on. Anybody can expand this series, right? Everybody knows how to expand this series, right? So you do that, and you get a series in et, and you can write it down for up to 100 terms or 1,000 terms because it is going down very slowly. You see, I did up to 10 terms and it did not go down very slowly. The second or third term is 10, but the 10th term is 4. It's going down very slowly. So you really need 100 terms, but I don't have paper that much to write it on. So I'm just going to stop right here at 10. And so I took the 10 terms, and now I generated basically, I'll generate in the next slide. But basically, so the coefficient of et minus k is this series. You write down d delta times delta plus 1, delta plus 2, and this is a gamma series, by the way. You can write down this whole numerator as gamma of 0.25 plus k divided by gamma of 0.25 because the series does stop here. So we have to put that in the denominator. This bottom is simply gamma k plus 1. 1 to k is gamma. What is gamma? Gamma is similar to factorial, except that when we say factorial k, we write down 1 to k, and this is gamma k plus 1. So gamma k plus 1 is k times gamma k. So basically, it starts 1 below factorial. So this is gamma k plus 1, but it's factorial k. This you cannot say factorial because factorial is defined only for integer values. So fractional values, you need gamma. Well, if you didn't hear gamma, we are going to use gamma quite a bit here, and you might just want to read up maybe in Wikipedia someplace. But it's very simple. It's just generalization of factorial for fractional values. Just like if you had a factorial which started from 5, you will write down factorial of whatever the last term is divided by factorial of 5 for that series. So this is only part of the whole factorial, right? Similarly, we are taking this gamma divided by that gamma to say that the series starts here and not at 1. And this notation is not really important because you can just do this in Excel directly without using any gamma function. You can just do it. How can you do it in Excel? You just type 10 terms like that. No, see, the thing I did it is basically is that you write down the first term and then you multiply that term by this last term here, minus 0.25 by 2. Then you multiply this whole thing by the last term, minus 0.25 minus 2 by 3. And you multiply the whole thing by one term. So you just multiply by one term at a time and you get the next coefficient. Right? And if you write it smartly enough, you just don't have to do every time. You just copy the whole thing. Just copy. You don't have to change manually anything. It will just take the previous coefficient and multiply by v minus k upon k. So you can write down this, and now you can see the sum of the basically so you can calculate xt that way, and where the xt would be sum of ETs, and the coefficients are given here anyway. And this, by the way, this xt as we generated here is also called fractional Gaussian noise. The ET is Gaussian, but this is not Gaussian. This is fractional Gaussian. I mean, xt is Gaussian. Sorry, xt is Gaussian, but it is not. See, the ET has no dependence. ETs are totally independent, identically distributed, right? xt has a dependence, and dependence is actually long term because xt depends upon xt minus 10, xt minus 12, xt minus 11, and so on and so forth. So this is called fractional Gaussian noise. If you look at the autocovariance of Fermat 0 delta 0, you will find this formula, which was on the previous slide. And then if you look at the autocorrelation, you get a much simpler thing because sigma square cancels out. You get autocorrelation by simply dividing the autocovariance by the variance, which is this one. So you get this as the autocorrelation. And mathematicians can solve this very easily because there is an approximation formula called Stirling's formula. For large P, you don't have to multiply anything. You can just calculate it in one sequence like that. And so for large K, they can show that this RK goes like this. C times K raised to 2 delta minus 1. C times 2 raised K raised to 2 delta minus 1. This whole thing, whole complicated stuff RK simplifies to this value, where C is something which we don't care right now. All right, C is some constant, which does not depend upon K. So, since this is what we are looking for. For the long range independence, this has to go 2 K raised to 2H minus 2 times a slowly varying function. So we found this a slowly varying function, which is constant actually. And the power of K is, instead of 2H minus 2, we have 2 delta minus 1. If we equate those two, 2H minus 2 equal to 2 delta minus 1, we get H equal to delta plus half. So whatever delta we choose, the H will be half more than that. We chose delta is equal to 0.25, H will be 0.75, and we will get LRD. Okay. If I would have selected minus 0.25 for delta, minus 0.25, H would be 0.25, it will be SRD. Okay, and you can see why. Let me show you. If in this formula, instead of 0.25, I put minus 0.25, right? When you bring it on this side, this will die down very fast. And you will see that if you expand all that. Anyway, so basically, what we are looking for is a series in which H is between 0.5 and 1. 1 is not interesting and 0.5 is not interesting. So it has to be strictly between 0.5 and 1, not at 0.5 and not at 1. And so that means you can use Fermat with delta strictly. All right. So now how do you generate LRD sequence? Now if you are doing any simulation and you know that there is an LRD, so either you can just use the trace that has LRD, or you can use Fermat to generate LRD. And you don't have to use the zero autoregressive part. You could use PDQ part to somehow match your process, and then plus delta part to match the dependence. So if you get, so basically what you do is you do it in two parts. First part is you generate ARIMA PDQ with integer D. D is integer. So we just generated a standard formula. Phi B, which is the exponent, this is polynomial in B, times 1 minus B raised to D. So this is the AR part, this is the integrated part, equal to A0 plus phi B ET, which is the moving average part. Psi B is the moving average part. So autoregressive, integrated, moving average. And then you can generate one of the two ways. Either you can just predict XT as a function of the previous XTs. So just do the autoregressive, or you can bring the whole thing down to this side and then expand like we did and get an infinite series and generate ETs, and from that you can generate XTs. So one of the two ways, it doesn't matter how you generate. Integer values would be easy, right? Now we do the same thing, except that instead of using ET, you use fractional Gaussian noise. Instead of ET, you use Fermat to generate something which we call YT or something. YT, YI. So we calculate YI, which are Fermat, and then instead of E's, we use those values so that we get the fractional values. Okay? So XT equal to A0 plus all of this times YI instead of EI. EI was the white noise. Instead of that, we put the fractional Gaussian noise. So now we get a fractional Fermat, fractional ARIMA. All right. And you will take 100 to 1,000 numbers. We took only 10 in our example, but that is again because we want just an example. If you are really generating this, you will need 1000 or 100 because there's a long range dependence and those coefficients don't die down very fast. All right. So let's see what we have learned so far. First, we learned that if the autocorrelation function adds to infinity, that means the xt is dependent upon past values, long past values. So that is why it's called long range dependence. Is that xt depends upon what was it yesterday, what was it day before yesterday, and so on and so forth. It's not memoryless anymore, right? And to generate that, we can use Farima. That's the easy part, is that we can just use fractional Farima where delta is between 0 and half. All right. And so we can generate the LRD sequences using Farima. And to do Farima, we just use Arima, except that instead of normal Gaussian noise, we put fractional Gaussian noise. All right. Normal Gaussian noise is independent variables. Fractional Gaussian noise is a set of long range dependent variables. Right? Noise. All right. So I think what we did, we just finished this. And so we take an example of generating that sequence. So I already did that. Basically, we want to generate this sequence. We expand it. And then I generated 60 random numbers, which were normally distributed. And I call them e minus 9 to e50. You see, I have to have minus values here. Because to get x1, I need e1, e0, e minus 1, e minus 2, and so on and so forth, e minus 9. So that to get x1, I need e minus 9. So I just go all the way here, e minus 9. Then for x2, I need up to e minus 8. So I generate 60 numbers, even though I need only 50 x values. To generate 50 x values, I generated 60 e values. These are normal distributed, so these are easy to find. And then I just use this formula to calculate x values. So these 50 values now will form a Farima 0.250 sequence. So as you can see, actually, I didn't really need any gamma function or anything. I just need to calculate these values. But I need to do it for 1000 terms or something, 100 terms. I just did it for 10. And I did it all in Excel, so I just have to write it so that I can just copy it up to 10 terms. Now, if I were to do it to 100, then I will need here like, minus 99 or something. So I will have to generate 100 extra normally distributed variable before I can start producing things. So the last thing that we are going to do in this whole class and this lecture is how to estimate H given a sample. So you measured something, sensor data, or anything else that you measured, and you want to show file sizes you measured process time or whatever. Don't measure file sizes because it's already measured now. Measure something different. and then you want to see what is H value. Is very simple. Is that you take the sample and divide it into pieces. A lot of pieces. Start with piece size of 1. All right. So if you have 100 observations, you will have 100 subsets, each of them size 1. Right. For each subset, find out what is the subset mean and what is the overall mean. So subset mean is basically, now let's just take instead of 1, let's take subset size of 2. So we have 100 observations. We divide into 50 subsets of size 2. Right? For each of the subset, we add those two numbers and we get this subset mean. Right? We get 50 means. All right? So that is what this is. XKM is the kth subsets mean, and we just take 1 upon 2 and we add up 1 plus 2 and then 3 plus 4 and then 5 plus 6 and so on and so forth. So we got 50 means like that. And out of those 50 means, we get the overall mean, which is basically we take these means and we add up 50 of them and divide by 50 to get the overall mean. All right? That's easy to do. We get 50 sample variances. For each sample variance, we take the mean and the overall mean, and then we divide by that. So we get actually one sample, not 50. We get one one variance for each value of m. M is the sample size. So for the subset size, if subset size is 1, we have 50 means. Out of those 50 means, we get one overall mean. And based upon these 50 means and one overall mean, we can get overall variance. Right? Then we do 2, subset size of 2, we get so many means and we get the variance of those means. We take subset size of 3, we get so many means, and we take the mean and the variance of those means. So we keep doing this as much as we can. Non-overlapping subsets. So that means that if you take 10 observations in the first subset, the next subset is the next 10 observations, not anything overlapping. This is called subsequence actually, what I was calling subset. So basically you calculate that and then all you have to do is plot log m, which is the size of the subsequence, as a function of the log variance. This is the sample variance. And the slope is 2h minus 2. So you see that log and then you see the slope. And basically if you have a line which has a slope of a1, then 2h minus 2 is equal to a1 and therefore the h is equal to 1 upon a1 plus 2, a1 by 2. So that is the h exponent. This method is called variance time plot method. Okay. And there are 10 other methods. All right. If you have to ever do this, you better pick up a book on long range dependence, such a thick book, and figure out all those 10 methods. For here, I'm just going to tell you one method, which is this method, which is simple. All right. But it is biased in the sense that the values that you get from here may be off from the real h value. All right. And second thing is that the process is non-stationary. It may not be self-similar or have LRD, but may still result in exponents. So this one assumes a stationary process. Okay. Now remember, long-range dependence process can be stationary. Self-similar processes are different, right? Some are stationary, some are not. Okay. So now here I think. So let's do that for the observation that we generated. 50 observations we generated. I did that. For m equal to 1, I calculated the mean, overall mean. I calculated the overall variance, and I took the log of this. Then I did sample sizes of 2, and I did the overall mean and the overall variance. And so I did this up to 10. Those 10 points I plotted. These are the 10 points here. And I fit a straight line. All right. The slope is minus 0.73. The slope of this line is minus 0.73. And therefore, my h value is 0.635. All right. Now you can see, actually, I had generated it with ARIMA, or actually FARIMA 0.25. Remember how we generated this whole 50 sequence? Right? So h value should have been 0.75. Right? H value is simply delta plus half. And the delta was 0.25. But why is it different? For two reasons. First of all, we have very small sequence, 50. If I would have generated maybe 5,000, maybe it would be closer to the real world, right? Second thing is I took a very small, I took only 10 values. Remember when we generated this sequence, we use only 10 up to e raised, the error values, you only use 10. You really need to use hundreds or thousands. So because of that, we didn't get exactly close to where we want to be, but at least, it is here. And I tried out this method with different values of here and there. They are similar, close to each other, but, slightly different. So this is the method for how to calculate H. All right. And if you have to really, as I said, if you have to really do this, then there are papers after papers and books after books as to how to do this. There are different methods, and some of them are very complicated, just too complicated for this class because you have to do frequency, spectrum analysis and things like that, which we didn't get into here. This is the simplest method, not the perfect method, but at least a starting point. If you find that this does pass your test, that it is more than, H comes out more than 0.5, then you need to read the book. Overall mean is slightly different, not that much different, but it's slightly different. For example, when you take the sample size of 10, it is 0.07 as opposed to 0.21. I mean, so they do change. Overall mean changes and the variance changes. Now, why does the overall mean changes? Let's see. Overall mean is simply compute the overall mean. This could be simply truncation error. I don't know. So, I think it is quite possible that the overall mean is because here's the thing, and Excel really calculates values to some this thing, and then we just cut it down to whatever number of digits we want. So overall mean will have a little change here. Would not be very different, but the variance is very different. I mean, So that brings us to the end of this whole discussion about the latest in network, latest in performance analysis. Is that basically heavy tail distributions have been found in many of the processes that we deal with. All right. And the heavy tail definition is very simple, that the tail is higher than the exponential. Or another way to say is that, if it is power tail is only subset of heavy tail. So, I mean, I think power tail will do most of the time. Power tail is Pareto. So if it is Pareto with alpha more than 1, that's what you're looking for. Second thing we learned about self-similar processes. And we don't really need to do much with self-similar. What we're really interested in is long-range dependence. Self-similarity simply means that as you scale in time, amplitude scales. And so what we need is long-range dependence, because long-range dependence is what is of interest to us. And that is that if the autocorrelation adds up to infinity. What that says is that X values are dependent upon long past. And how do you get that long range dependence? How do you generate that? ARIMA would do that. ARIMA with fractional values of delta would generate that, particularly if the delta is between 0 and half. With 0 and half, you will get H value, and H is the Hurst parameter, which is the key to all this. And the Hurst parameters will be between 0.5 and 1 for long range dependence. And it can be estimated using that variance time plot that we just did. There is a lot about self-similarity that I didn't cover because we really don't need that. What we really, as I said before, what we need is LRD. All right. And a lot of people confuse self-similarity with LRD. And so instead of saying that file sizes have LRD or the network traffic has long-range dependence, they will say the traffic is self-similar. That does not say whether it is long-range or not long-range. And so we are only interested in those processes that have long range. So here, self-similarity was explained simply to explain this part, that time and magnitude scaling. All right. And much more about that is there in the books on statistics, but we are really not interested in that part. We are really interested in long range dependence and heavy tail. Those are the two things. Now, given a process, how do you show it is self-similar? I'm sure there must be some methods, but we haven't got into that here.